The concept of the boundary of the observable universe has long captivated the minds of scientists, astronomers, and those with a curiosity for the cosmos. It raises profound questions about the very fabric of space, the organization of the cosmos, and whether our universe ends at some point or stretches into infinity. With the development of groundbreaking observational tools, chief among them, the James Webb Space Telescope, JWST, humanity's pursuit of answers to these age-old enigmas has surged forward. Thanks to its extraordinary engineering, the JWST is capable of detecting minute and intricate details from faraway regions in space, making it possible for researchers to peer deeper into the cosmos than ever before. To fully appreciate the importance of these insights, it helps to clarify what astronomers mean when they refer to the observable universe. This phrase describes the segment of the cosmos we can detect using current technology, whether via Earth-based observatories or telescopes orbiting in space. It includes all celestial bodies whose light has had enough time to reach us since the birth of the universe. Within this region lie countless galaxies, solar systems, clouds of gas and dust, and much more. However, this observable zone represents just a sliver of a possibly infinite universe, most of which remains inaccessible to us for now. Scientific assessments estimate the observable universe to span a diameter of around 93 billion light-years. A single light-year, the distance that light travels in 1 year, is approximately 5.88 trillion miles or 9.46 trillion kilometers. Multiply that by 93 billion, and you get an almost inconceivable figure, about 5,468 trillion kilometers. Such staggering distances underscore the truly immense scale of the universe. This colossal expanse finds its origin in the widely accepted Big Bang theory. According to this model, the universe burst into existence around 13.8 billion years ago from a hot, dense singularity that rapidly expanded. In the eons that followed, the universe continued to grow, influenced by unseen components like dark matter and driven by a force still not fully understood, known as dark energy. In the chaotic moments after the Big Bang, matter began cooling, allowing particles to form atoms, which then coalesced under gravity's pull to create stars and galaxies. Over time, these structures became increasingly complex, giving rise to clusters of galaxies, solar systems, and planets. Despite this rich cosmic tapestry, the majority of space remains void. To illustrate this emptiness, imagine shrinking our solar system to the size of a coin. The nearest star would then be located 2 soccer fields away. And this pertains solely to the Milky Way, one among billions of galaxies within our observable range. So why can we only perceive a portion of the universe? 2 primary reasons explain this limitation. First, light travels at a finite speed. When we observe distant galaxies, we aren't seeing them as they are today, but as they appeared eons ago. In essence, gazing across space is like peering through a time machine. The more distant the object, the older the light that reaches us. Second, the universe is undergoing continuous expansion. A helpful analogy is to imagine dots on the surface of a balloon that's being inflated. As the balloon grows, the dots move farther apart. This is similar to galaxies drifting away from each other as the fabric of space expands. Furthermore, light from these far-off galaxies gets stretched due to this expansion, a phenomenon known as redshift. Eventually, some galaxies become so remote and their light so redshifted that it can no longer be detected, placing them beyond our observational reach. This introduces one of the most compelling inquiries in modern cosmology: what lies beyond the edge of what we can observe? Philosophers and scientists alike have wrestled with this question for centuries, proposing various hypotheses about the universe's architecture and whether a boundary even exists. One popular viewpoint suggests that the universe is infinite and unending, grounded in the cosmological principle that posits uniformity in all directions. If this is accurate, the universe has no traditional edge and stretches indefinitely. Another idea holds that the universe, while finite in size, is unbounded, akin to the surface of a sphere. In this model, if you could travel straight in any direction long enough, you would eventually return to your starting point, much like circling the Earth. A third and highly speculative concept is the multiverse theory, which asserts that our universe is just one bubble among many in a vast cosmic foam. According to this view, countless other universes exist, each governed by different physical laws and conditions. Some might be similar to our own, while others could be radically different. Though these concepts are largely theoretical, advancements in space observation are gradually transforming speculation into potential reality. This is where the James Webb Space Telescope becomes indispensable. The JWST is already revolutionizing our perception of the cosmos. Designed to examine the earliest epochs of the universe, it can look farther back in time and deeper into space than any previous observatory. By focusing on the infrared portion of the electromagnetic spectrum, the telescope captures ancient light that has been redshifted over billions of years as the universe has expanded. One of the most astonishing revelations from JWST involves the discovery of 6 extraordinarily massive galaxies that appeared only 500 to 700 million years after the Big Bang. These galaxies were spotted in the telescope's earliest deep-field images and have upended conventional wisdom in cosmology. The study detailing these findings was published in the journal Nature and has caused widespread astonishment in the scientific community. Before this discovery, prevailing theories held that the early universe contained small, nascent galaxies slowly assembling mass via star formation and mergers. The dominant models indicated that it would require billions of years for galaxies to accumulate enough matter to rival the size of the Milky Way. The galaxies revealed by JWST, however, seem to be not only fully developed but also enormously massive, even rivaling or exceeding the Milky Way in stellar mass. This unexpected discovery challenges foundational assumptions about the speed at which matter can collapse and form large-scale structures. If these galaxies truly are as mature and massive as they seem, it implies that star formation occurred at a dramatically accelerated pace in the early universe, a rate not currently explained by existing models. Alternatively, it could indicate deeper misunderstandings in areas such as dark matter behavior, cosmic inflation, or the basic timeline of the early cosmos. The presence of such enormous galaxies so soon after the Big Bang is one of the most compelling indicators that we may be on the cusp of a paradigm shift in our understanding of galaxy formation and cosmic evolution. Some of these newfound galaxies possess stellar masses approaching 100 billion times that of our Sun. For context, the Milky Way contains about 60 billion solar masses. This raises a pressing question. How did such titanic structures form so quickly? The Hubble Space Telescope, which previously held the title for deepest space observation, had identified a few early galaxies, but they were diminutive and faint in comparison. The galaxies now visible through JWST suggest that star formation rates in the young universe were far more intense than previously thought, or perhaps that our framework for understanding early cosmic development needs to be re-examined. These groundbreaking observations were made possible by JWST's cutting-edge infrared sensors and spectroscopic tools. These instruments allow researchers to analyze the composition, distance, and configuration of distant galaxies in detail. Many of the early galaxies identified show evidence of rapid star formation and possess unexpectedly mature stellar populations. The implications are monumental. If current models fail to account for the existence of such rapidly forming galaxies, then those models must be adapted. This introduces possibilities ranging from altered star formation processes and accelerated galactic mergers to fundamental errors in our assumptions about early universe physics. Adding to the mystery is the notion that some of these observed entities may not even be galaxies in the conventional sense. The JWST's unprecedented resolution could be unveiling entirely new phenomena, hinting at objects or structures never before documented. This broadens the horizon of cosmological research in ways previously unimaginable. Nicknamed universe breakers by many in the astronomical field, these massive early galaxies are rewriting the foundational rules of cosmology. They challenge more than 99% of the existing theories about how galaxies formed in the early universe. The long-held belief was that galaxies originated as small star and gas clumps that gradually merged and evolved over billions of years. The JWST's observations, however, suggest that in some scenarios, galaxy formation was an incredibly swift process. Remarkably, These galaxies were found in the very first sets of images returned by JWST in mid-2022. Scientists were stunned to see such complex formations so early in the telescope's operational life, surpassing even the most ambitious expectations. These discoveries have reignited fundamental debates and encouraged new lines of inquiry. Could the universe's structure inherently allow for such rapid galactic development? Are there unknown forces or physical principles influencing early cosmic growth? Might our methods for measuring cosmic time need to be revised? While definitive answers remain elusive, what is certain is that the James Webb Space Telescope is extending the limits of what humanity thought was observable. It is not merely offering solutions to old questions, but is also introducing new puzzles that will occupy researchers for years to come. Because JWST can observe light from nearly 13.5 billion years ago, just a few hundred million years after the Big Bang, it occupies a unique position in astronomical studies. Considering that the universe is estimated to be around 13.7 billion years old, JWST is essentially looking back in time to the universe's infancy. This ability has the potential to revolutionize our comprehension of the observable universe. Not only do these observations question established models of how galaxies form and evolve, but they also prompt a reevaluation of our understanding of time, space, and the structure of the universe itself. It could be that the boundaries of what we consider the observable universe are more fluid and dynamic than once believed. In essence, the James Webb Space Telescope is doing more than observing distant galaxies. It is unveiling the fundamental story of the cosmos. It is stretching the frontier of the observable universe and enabling astronomers to reconstruct the earliest chapters of cosmic history. Through its data, we aren't merely seeing stars and galaxies. We are witnessing the universe narrating its own origin story. As JWST continues its mission, the possibilities of what it might uncover remain limitless. Could there be more universe breakers concealed in the furthest corners of space? Might we finally glimpse the edge of our observable universe? If such a boundary exists, is it even possible that we may one day detect signals or signs from other universes, or discover new forms of cosmic matter unlike anything we've imagined? Only the future and the unyielding eye of the James Webb Space Telescope can provide those answers. But what is indisputable is that we are living through a new golden age of astronomical discovery. This era is not only enhancing our knowledge of the cosmos, but also reshaping our understanding of our place within it.